There seems to be a lot of smoking. This doesn't be fine. All right, was everybody able to get these three done? Or at least. All right. Can everybody at home hear me okay? You guys hear me? Thank you. All right. Then let's go ahead and start. We want to first do that square root of n over 1 plus n to the 3 halves. Which method of determining convergence would we use for that? Which test would we use here? Yeah, I think the integral test is probably as of right now, it's probably the only one that we could use. But it's gonna be the easiest, probably the quickest way to do that. All right. Faulty. All right, so we're gonna try to use the integral test for the first one. So what three things do we have to show first before we're actually even allowed to try to use the integral test? Because remember, it has to satisfy three properties. And then beyond that, it actually has to tell us something once we do the integral. We have to actually be able to do the integral and evaluate it, which can be difficult. So what's the first thing that we have to check?
always come to the x greater than. Greater than.
Yeah, so we have to check that, the function. Well, this is what we'll do first, we'll, look at our series, which we know is the sum from n equals 1 to infinity of square root of n. Divided by 1 plus n to the 3 halves, so we're gonna let f of x be the function square root of x divided by 1 plus x to the 3 halves. But now we have a function defined in terms of the series nth term. So we need f to be positive for all x greater than 1, or it doesn't really have to be 1, it just has to be some number. And then everything after. So it should work for 1. Is that true? Well, we know that if we plug in a positive number on the top, that's all we can plug in. We're gonna get a positive. The denominator is always gonna give us a positive if we plug in a positive, so that's gonna check out for sure. And then secondly, we need to check what? If it's continuous for x greater than or equal, well, greater than 1, so we wanna check if f is positive, continuous. And then we'll check the third one in a second, so it's definitely continuous. And we can see that very clearly because if we plug anything in, it's not gonna break this, right? If I plug in a positive number, I'm not gonna get 0 in the denominator or anything weird happening, so that checks out. And now for the harder part, we have to check that it's decreasing, right? So is f decreasing for x greater than, well, x greater than 1, or greater than or equal to 1. Doesn't make a difference for us here, but this is where it becomes a little bit more difficult, because if we wanted to show this is decreasing, we could try doing it with the nth term of the series. That would look like this though. We'd have to remember that decreasing means that a sub n is greater than the next term, which is a sub n plus 1. So if we wanted to show that this was decreasing using the nth term, we'd have the square root of n over 1 plus n to the 3 halves is greater than square root of n plus 1 divided by 1 plus n plus 1 to the 3 halves. I don't know how we could do that very easily and get to a statement that we know for sure is true for all positive n. The easiest way to approach this might be using Calc 1. So if we find the derivative of f prime of x is going to give us, and we have the bottom squared, so 1 plus x to the 3 halves squared. And then we have the bottom function times the derivative of the top, which is going to be 1 over 2 square root x. Minus the top function. Times the derivative of the bottom, which would be 3 halves x to the 1 half. All right, so let's simplify this now. We're gonna have in the numerator 1 plus x to the 3 halves divided by 2 square root x. And then the next term we're subtracting here would be a 3x divided by 2. Do we agree? 3x over 2. And we need a common denominator, so we have the 2, we just need a square root x, so we're going to multiply this thing right here by square root x over itself. And then we still are dividing that whole thing by 1 plus x to the 3 halves squared. All right, any questions so far before we keep going? Alright, so let's simplify, and then remember, if we divide a fraction by a fraction, we are multiplying by its reciprocal. So what we have here is 1 plus x to the 3 halves. And up top here, we're gonna get 3x to the 3 halves. And we're dividing that whole thing by 2 square root x. And then we will divide that by that 1 plus x to the 3 halves squared. Which means we're gonna be multiplying it by 1 over 1 plus x to the 3 halves squared. Okay, so what do we get now? We get on top, we get a 1 minus 2x to the 3 halves. And in the denominator, we're gonna have square root x. So square root x times 1 plus x to the 3 halves squared. All right, so let's just break this down real quick, because we need to show that this is decreasing, so we need to show that this derivative is gonna be negative for all positive x, basically. So if we take a look at this, what do we know about 2 square root x? If we plug in any number to it. Anyone? 2 square root x? Isn't that always positive? No matter what we plug in? So that right there is gonna be positive. All right, what about the next one? We have 1 plus x to the 3 halves, and we're squaring that. Well, we know that if we square anything, we get a positive, right? So that whole thing down there now is gonna be positive. And then in the numerator, if we plug in any positive number, we're gonna have some number to some power subtracted from 1. Well, times 2 subtracted from 1. So really, 1 minus 2x to the 3 halves, if we wanted that to be negative, so that the whole thing is negative, that would mean that 1 is less than x to the 3 halves. We divide 2x to the 3 halves, we divide by 2. So we'd have 1/2 is less than x to the 3 halves. And then we could raise both sides to the 2/3. So 1/2 to the 2/3 is where that begins. So for everything greater than 1/2 to the 2/3, which is a pretty small number, this thing is gonna be negative. We don't even have to do that, we can see it clearly just from looking at the numerator, but that at least shows us exactly what it is. So up top here, we know that we have a negative. And so we have negative divided by positive, that tells us that f prime is negative for all x greater than whatever number that was, 1/2 to the 2/3, I think, but we just need it to be 1. So this implies now that f prime of x is negative for x greater than 1, and this implies now that f is decreasing. So now we can actually get to the test, which we're gonna do now. What is it to look at the improper integral from 1 to infinity of square root n, well, square root x divided by 1 plus x to the 3 halves dx. So we can change this and make it the limit as n b approaches infinity. The integral from 1 to b of, I'm just gonna write this as x to the 1/2 on top, divided by 1 plus x to the 3 halves dx. So how do we evaluate that integral? Anybody get this one? That's a simple u sub, isn't it? We're gonna let u equal 1 plus x to the 3 halves. So du dx would be 3 over 2x to the 1 half. That means that du is 3 over 2x to the 1 half dx. And then if we wanted to solve for dx, we could multiply both sides by 2/3 and then divide by x to the 1 half. So we'd end up with 2 over 3x du is equal to dx. All right, so when we replace now, I'm just gonna do an integral on the side and then we'll come back and actually do the improper part of it. But we have the integral of, and up top we have the square root x. Or x to the 1 half. And then in the denominator, we have u. And then instead of dx, I want to write 2/3. X to the 1 half goes with the 3. Du. Now the x to the 1 half will cancel. We're left with the integral of, well, 2/3 times the integral of 1 over u du. And so this gives us now, we know this thing integrates to become what? Yeah, 2/3 ln u. Plus c. So let's go back to the improper integral. So we have the integral from 1 to infinity of x to the 1 half divided by 1 plus x to the 3 halves dx. And we said now that this is going to become we pull out the 2/3. And then we'd have the limit as b approaches infinity of ln of u, but u is really what? 1 plus x to the 3 halves. And that's going to be evaluated from 1 to b. So we have here 2/3. Limit as b approaches infinity. And this is going to be now ln of 1 plus b. Ln of 1 plus b to the 3 halves. Divided by minus ln of 1 plus 1 to the 3 halves. This just died on me. I thought that was charging. It's good. All right. The limit as b approaches infinity of, well, 2/3 of ln of 1 plus b to the 3 halves minus ln of 1 plus 1 to the 3 halves. And so what happens here? Any ideas? Well, as soon as we plug in infinity for this b, this whole thing's going off to infinity, right? So this thing should give us 2/3 times, this is gonna be infinity. And then that's gonna be, doesn't matter, who cares, because this is just gonna be infinity, so it diverges. And that means now that by the integral test, we can say that, this series diverges as well. All right, any questions about that one? All right, what was the next one? N over n plus five?
Yeah.
So the next one was the series from n equals one to infinity of n over n plus five. Anybody get this one? It converges and diverges?
Said it diverges, but I don't know if I did it right. I think so.
What test did you use?
So we can kind of look like a, we see.
It's almost a P series. But when if we tried to make it look like a P series, it would actually cancel out a little bit. What other really easy tests do we have? What's that?
Use that. Yeah.
Yeah, the term test. So what does the nth term test say? Says that if the limit is not zero, if the limit as n approaches infinity of a sub n is non-zero, then what? Then the series diverges, right? That's the theorem. And so if we tried to find the limit of this thing, the limit is n approaches infinity of n over n plus five. Well, this is a case where we would have to, from calc 1, we'd have to divide by the highest power of n. So this would be, the limit is n approaches infinity. Highest power is just n to the 1, so we're going to divide everything by n to the 1. So we get n over n divided by n over n plus 5 over n. And now if we simplify that, what we have here is the limit as n approaches infinity of 1 divided by 1 plus 5 over n. And that gives us 1 divided by 1 plus 5 over infinity. That whole term goes to 0. And so our limit is 1, which we know is not equal to 0. And so by the nth term test, this thing diverges. So therefore, the series n over n plus 5 diverges by the nth term test.
Here are matches for end of divergent.
What? My phone talking. I haven't even touched it in like an hour. All right. Any questions about that? Everybody at home okay? Everybody still alive? Okay, the next thing we wanted to do was, what was the number that we had to write as a fraction 0.417 or something? Is that what it means? You guys remember? We wanted to write, let's see it. Was it 0.417 or 517? Remember,
It was 0.4.
417? All right, so we want to write 0.417, repeating as a rational number. So, that means that we have to write it in its expanded form, so we know that this is gonna be equal to. What, 4/10⁻⁻, plus 1/10⁻², plus 7/10⁻³. And that would give us the 0.417, the first one, right? Now we have to go to what? The next four, which would be 4 divided by 10⁻⁴, 1 divided by 10⁵, 7 divided by 10⁶, and so on. So we can write this by, well, is there anything we can factor out here? The square? Yeah, there's a, this is 1/10 that we could factor out at first, but. If we actually combine these things. Because if we think about what we have here. Right here we have 417 divided by 1,000, right? So 10 cubed. And then we have the next one, which is 417 divided by 10⁶. And then the next one would be 417 divided by 10⁹. And then that's gonna go on forever. And eventually, we're gonna hit 417 divided by 10 to the, well, how would we write these numbers generally? We know an even number is 2k and odd number is 2k plus 1. But how would we write one of these? It's just a multiple of 3. So we could just write 3. And then beyond that. So we could factor out a 417 divided by 10 cubed. And then we'd be left with what? We'd be left with a 1 from the first term. And from the second term, we would be left with what? This is where we have to be careful. Well, a 1 on top. And then in the denominator, we would need a 10 to the what? Right? We need a cube, because when we multiply through that 10 cubed, we need it to add up to 6, the exponent. So the next one would be 1/10⁶, right? And that's gonna keep going forever. All right, so our value of A in this case is gonna be 417 divided by 10 cubed. And then our value of R, our common ratio is 1/10⁵. Alright, so if we want to figure out what the rational number is gonna be, we're gonna have A/1 minus R, so A divided by 1 minus R would be 417 divided by 1,000. Divided by 1 minus 1/1000. And if we simplify that, we're gonna get 417 over 1,000. And the denominator here would be 1,000 over 1,000 minus 1 over 1,000, so that's 999. over 1,000? And we are going to multiply by its reciprocal, right? And so we get 417 over 999. Questions? Right. So we are at like, I think we're like almost halfway through the series test, but we have the somewhat harder ones coming up now. Um. Let's do this. I'm gonna give you 3 more series and not tell you what kind they are, or how to actually find the convergence. I'm gonna ask you to work on those for a few minutes. If you need to take your break at some point, you're welcome to. It's 10:10 right now, so we'll start these at like 10:25. We'll go over them at 10:25. So work on these for a few minutes and see what you can come up with. And like I said, if you need to step out for a moment, feel free to do so. I wanna get back to these right after that. All right. First series is gonna be one over n to the square root 2. To determine if the series converges or diverges. One over n to the square root 2. Um, Series n squared e to the negative n cubed. 5 minus 2 squared n over n cubed. Alright, so there are the three. Please give these a legitimate try. Charge so I can use the iPad. How are these going? You guys get these? These are kind of tough. Did anybody get through all these? No. Just a hint. You need it. We can write this as the series n squared over e to the n cubed. And that's how we can start that one. You can see that if you would let u, I guess maybe you wouldn't even have to write it that way, would you? Because you can just let u equal negative n cubed and do an integral test. Now for this one actually ends up being a lot easier. And it looks, we'd have the series from n equals 1 to infinity of 5 over n cubed. Minus the series from n equals 1 to infinity of 2n squared, 2 squared n over n cubed. And then we would go ahead and try to simplify that a little bit more. We should end up with 2p series and we're subtracting 4. So for the first one, we have 1 over n to the square root 2. And what kind of series is that? Yeah, it's a p series. Our p value there is square root 2. And what do we know about square root 2? (1.414), right? So really we have 1 over n to the 1.414. So our p value here is greater than 1. So that means it does what? Converges if p is greater than 1. Alright, so the next one. We have n squared times e to the negative n cubed. So there's a lot of different ways, I guess. We could look at this. I don't know. If anything would be easy. Besides just trying to do an integral test on it. Yeah, that's what I would try to do there. But we'd have to actually test to see if the integral test can be applied to it. I guess that's. Be all right. Did anybody try to use the integral test in this? The conditions work out? Okay. Trying to find a problem that was really similar to this one, but I can't seem to find it. It's just got different powers of n. Yeah, so if we try to do the integral test here. First, is it gonna be positive? Well, e to anything. Is, if we just look at the graph of e to the x, y equals e to the x. It's always positive, right? It's always above the x-axis. So that e part, even if it's negative, it has a negative exponent, it's still gonna give us a positive result. So that is gonna be n squared, which is positive, times e to the negative n squared, which is positive, so every term is gonna be positive, so that checks out for us. Then we'll have, what I was thinking of isn't like that one at all. Then we'll have to determine if it's continuous, nothing breaks there. And is it decreasing? So that's again the hard part, we have to show this thing is decreasing. So I will try to use, did you show it using Cap 1? Yeah. I guess we'll find the derivative and everything, so. We'll have, we'll have to let f of x be equal to x squared, e to the negative x cubed. And so if we try to find the derivative f prime, we're gonna have f prime of x is equal to, and it's a product rule. So we're gonna have derivative of x squared, which is 2x, e to the negative x cubed, plus the derivative of the second function, which is gonna be e to the negative x cubed times the derivative of negative x cubed. That's a chain rule. So the derivative of negative x cubed is negative 3x squared. So we're going to get a negative 3x squared e to the negative x cubed times x squared. And now to be 2x e to the negative x cubed minus 3x to the 4 e to the negative x cubed. And we can factor out an x e to the negative x cubed. We'd be left with inside a 2 and a minus 3 x cubed. Okay. So remember, all of our x's are greater than 0 here. So if we plug in anything to this, that's greater than 0, that 2 minus 3 times something greater than 1 is always gonna be negative, right? And then this term is positive times positive, so we're always gonna get a negative here, so we just showed that f prime is negative, and so the integral test applies. So this is positive, this is negative, so we could say f prime is negative for all x greater than 1. And so the integral test applies, so we're gonna have the integral from 1 to infinity of x squared e to the negative x cubed dx. And if we do the u sub for that, we could let u equal negative x cubed, so du would be negative 3x squared dx. If we solve for dx, we have du over negative 3x squared. So our integral now becomes x squared e to the u du over negative 3x squared. And those will cancel, so we're left with negative 1/3 times the integral of e to the u du, which is going to give us negative 1/3 e to the negative x cubed. And so when we go over here, what we end up with is the limit as b approaches infinity of the integral, which we said was negative 1/3 e to the negative x cubed, evaluated from 1 to b. And so we can pull out that negative 1/3. Now we would have e to the negative b cubed minus e to the negative 1. So that's going to be 1 over b cubed minus, oh, I can't forget my limit symbol, can I? LIM up front, it's very important. So what happens here is we get negative 1/3 times 1 over b cubed minus 1 over e. 1 over e to the b cubed, sorry. One over e. Okay. So what's going to happen with this thing now? Does it converge or diverge? Yeah, negative, well, 1 over e to the b cubed, that's going to be 1 over e to the infinity, so that's going to go off to infinity, the denominator, and so the whole thing. And what we're left with here is positive 1 over 3e, looks like, right? So that's what it's going to converge to. It doesn't matter what it converges to here, but it tells us that the integral converges, and therefore the series that we were looking for converges as well. All right. And the last one, could you read me the last one that we had? It was 5 minus 2 square root n?
Over n cubed.
N cubed? Thank you. All right, so for this one, we would have the sum of 5 over n cubed minus sum of 2 square root n over n cubed. So this right here is really when we have square root of n over n cubed, that's n to the 1/2 over n cubed. So n to the 1/2 minus 3 would be n to the 1/2 minus, and 3 is really 6 over 2. So it'd be negative 5 over 2. So we get 1 over n to the 5/2, right? So this thing is going to be 5 times this series of 1 over n cubed minus 1 over n to the 5/2. These are both greater than 1, they're both p series. And so they're both greater than 1, so that means that they do what? If it's greater than 1, they converge, right? So these are both convergent p series, so if we add 2 convergent series together, we get a convergent series. All right, we're gonna define two more tests. Actually, how many tests do we have to do here? I'm sorry, one test today. Yeah, just one more test and then, we'll be good. Let's do that. And again, if you could try to work on the homework, this is not, this is no joke, this chapter. It takes a lot of practice. And, if you try to do it last minute, it's really not gonna work. It just takes a lot of staring at the problems and trying to figure out what's happening and trying to use the right tests. So please start this. We're looking at something called the direct comparison test. And that means that if we can't figure out what a series is doing, if it's converging or diverging, we're just gonna look at something that we do know and try to compare it. And it ends up being a pretty easy thing to do. All right. Here is the direct comparison test. That's not it. No. No. Oh, come on. That's why I wanted to connect it to the computer. All right, good. So I'll give you a second to copy this down. Please. Here it is. So when we showed that those functions were we had to basically compare a sub n with a sub n plus one, and that's kind of what's gonna happen here. We just have to compare a series with a different one. So what this theorem says is that if we have two separate series and we are able to compare their nth terms, and when we do that, we get a sub n is gonna be smaller than b sub n. Now, keep in mind, when we show functions in an inequality, it takes a lot. We have to actually show that it's true, not just saying it's true and going with it. So this says that if a sub n is the smaller of the two series, then if series b sub n converges, then a sub n converges, and if a sub n diverges, then b sub n diverges. So what that means is when we compare these two things, if we have the smaller one that is divergent, remember the if-then statements are, we can't say it goes both ways, so if the smaller is divergent, then the larger is divergent. If the larger converges, smaller converges. That's what this is saying. All right, so let's look at an example. We want to determine if the series converges or diverges, and we're given the series from n equals 1 to infinity of 1 over 3 plus square root n. And then our second one that we're going to look at is 2 plus 3 to the n divided by 2 to the n. Write that down. 2 plus 3 to the n divided by 2 to the n. All right, so let's take a look at these two. I want to do the second one first because it's a little bit nicer. So the second one was 2 plus 3 to the n divided by 2 to the n. All right, so if I asked you to determine if that second one converges or diverges, you wouldn't really know what to say, right? There's nothing that we've done so far that actually would enable us to analyze that thing. But the first thing that we should notice is that it looks really similar to what series? Meaning if we could make a small change to this to make it look manageable, what would that small change be? Any ideas? Yeah, exactly. You're exactly right. It almost looks like the geometric series. So if I got rid of that three, I'm sorry, the two on top, it would be geometric, right? It'd be three halves to the end. So let's just think about this real quick. We're gonna write that down actually so that we know why we're choosing that, but this thing looks a lot like the geometric series. I'm just gonna say it looks similar to the series three to the n over two to the n. And what if we have three to the n over two to the n? That's really three over two to the n. And what kind of a series is that? It's a geometric and it does what? Converge or diverge? If r is greater than one, it diverges, right? So this looks really similar to this thing, which is three halves to the n. And that is going to be a divergent geometric series ruler. And that's also, this is also a really good example of why we need to know how to handle these. And we have to be able to recognize that this three over two to the n is actually a geometric series. So this is a divergent geometric series. Okay, so why don't we choose that as our comparison? And we'll see if we can actually compare these two nth terms. So if we have two plus three to the n, can we say that this is true? For all positive n, definitely, right? And then if we divide by a positive number, it's still true, right? By both sides. So this tells us that two plus three to the n over two to the n is greater than three to the n over two to the n. Everybody okay with that? We started with a fact, which is if I have the same number on both sides and then I add two to one, that's going to be larger. And then I can divide both sides by a positive number. And now what we have is right here. I'm not going to use A and B because we did that in the theorem. I'm just going to call this one C sub n. And then over here on the right, we'll call that D sub n. We don't even have to name them, but we don't know what this one does, right? The left-hand side, we don't know what it does, but we do know what the right-hand side does. That right-hand side is the one that diverges, we said. So if the smaller diverges, does the larger diverge according to the theorem? That's exactly right. So the direct comparison test says that if the smaller of the two if the smaller diverges, then the larger diverges. So since that inequality is true, so we can say since 3 to the n over 2 to the n is smaller than our series of, which is 2 plus 3 to the n over 2 to the n. Series we're looking for is divergent by the direct comparison test. Two plus 3 to the n over 2 to the n diverges. Any questions about this one? All right, so the last one here is 1 plus, or 1 divided by 3 plus square root n. And what does this one look like? This looks similar to the series n equals 1 to infinity of 1 over square root n, right? You just take away that 3 and that's what it looks like. So what kind of a series is this one? It's a P series because this is really 1 over n to the 1/2, right? So it's similar to this thing, which is the sum from n equals 1 to infinity of one over n to the 1/2, which is a P series that does what? P is less than 1, right? So it converges, or does it diverge?
Divergence.
Diverges. So let's compare these now. We're gonna start with a fact, which is that if we have 3 plus square root n, we know that's larger than square root n, right? And then remember when we worked with the reciprocals last time, we said if we look at this reciprocal, the sign flips. So that means that 1 over 3 plus square root n is less than 1 over square root n. All right. Well, we're kind of there, right? I mean, that's our inequality. We know that this one right here is a divergent P series. Oh, I got something in my eye. What can we do with this? Anything? Yeah, we're kind of doomed here, right? Because what's happening is the larger of the two series is the divergent one. And that's not what the theorem says. The theorem says that if the divergent one is the smaller of the two, then the other is going to diverge. But if it's the larger, the direct comparison test fails here with that choice. So the direct comparison test fails with this choice. Are there any questions? So we need to try to fix it somehow. Meaning we need a new comparison. So what else can we compare it with? Any ideas to what compare this thing to? It might be too complicated. Just think about what we'd have to do there, we have to raise it to some number, but think along the P series. We could try to compare it with well, maybe 1/n. So if we have 3 plus square root n, and we want to know, well, we do know that 1/n diverges, right? So that means that we want to try to show that 1/n is smaller than 1/3 plus square root of n. So if we can show that this is true, 1 divided by 3 plus square root n is greater than 1/n. Then we know that the smaller one diverges, and so the larger one would diverge. The problem is showing this is true. So I do know that if I look at the reciprocals, I would have 3 plus square root n is less than n. And I want to try to see where that's true. So we could try to solve this thing. It doesn't end up working out very nicely. But if we just plug in values, we can see what's happening. So if I plugged in like 4, I would have the square root of 4 plus 3, that would give me 5. But on the right, I would have 4, right? So up to 4 is not going to be true here. But then the next one, if I plugged in 5, now I need a calculator for that square root. Let's just go up to 9. 9 would be 3 plus 3 on the left, 9 on the right. So this is true for n equals 9. And somewhere between that actually happens. I think it's like 5 or 6 or something. But we can end up showing that this is a true statement for n greater than we'll just say 6. I think that's the correct. But it doesn't matter because it's eventually true and it's going to be always true after that. So we know this is true now. Any questions so far? So let's go ahead and finish it then. We know that 3 plus square root n is less than n for n greater than 6. And that means that 1/3 plus square root n is greater than 1/n for n greater than 6. So here we have a divergent P series that's smaller than R series, and we were actually able to show that it's smaller. So we can say therefore, the series 1/3 plus square root n diverges by the direct comparison test. This problem is a bit of a stretch. I mean, it works. We end up making it work, but you would not normally look at 3 plus square root n and think to compare it to n. It's just the only reason we had to do that is because the first way failed. But if this one failed too, we might choose a different test and just see if we can do something better. Any questions about this? Alright, so what we've done so far is we started with telescoping. After that was so we had a telescoping series, we had geometric. What else did we have? Series. Integral test. Anything else? Right. Series, telescoping, geometric. And now the direct comparison test. So next class, we're gonna do something called limit comparison test, and then we're also gonna look at alternating series. Let's go back and forth between some. All right, have a good day, everybody. I'll see you guys.